Right now, a companion star up to 3 times heavier than our Sun is plowing directly through the superheated outer layers of Betelgeuse. For over a century, astronomers observed this red supergiant dimming and brightening on an unyielding 6-year cycle, unable to explain why a single pulsating sphere would behave with such mechanical rhythm. In late 2024, specialized imaging finally pierced the blinding glare of the Orion constellation and confirmed the phantom partner. An unseen stellar body carving a massive gravitational trench through its neighbor's atmosphere, yet this discovery introduces a far more unsettling mystery. When Betelgeuse unexpectedly lost 2/3 of its luminous output in 2019, skywatchers worldwide believed they were witnessing the final collapse before a daylight-visible supernova. The culprit was not an impending explosion, but an ejection of planetary mass that left researchers bewildered. And that gap in the data is exactly what this companion star's orbital path might finally decipher. To make sense of what just happened, you need to understand the colossal scale of this stellar neighbor. Betelgeuse marks the prominent reddish-orange shoulder of Orion, sitting roughly 650 light-years from Earth. Ancient star catalogs across Mesopotamia, Greece, and dynastic China tracked its distinct ruddy hue. For thousands of years, humans assumed it was a solitary cosmic titan, drifting through the interstellar medium. It belongs to the rare category of red supergiants. These are aging stars that have exhausted the primary hydrogen reserves inside their cores and swollen to grotesque proportions. If you dropped Betelgeuse into the center of our own solar system in place of the Sun, its outermost atmosphere would swallow Mercury, Venus, Earth, Mars, and the entire main asteroid belt extending out toward the orbital track of Jupiter. A commercial airliner traveling at standard cruising speed would take over a millennium just to circle its equator once. Because of this physical bulk, Betelgeuse behaves like an unstable thermal engine. Its outer envelope breathes. The star pulsates inward and outward on a well-documented fundamental period of roughly 400 days. As it compresses, it heats up and shines brighter. As it expands, it cools and dims. Yet alongside that regular 400-day rhythm, long-term observational records stretching back across generations of ground-based astronomy captured a secondary, much slower oscillation lasting roughly 2,100 days, nearly 6 full years. Standard stellar astrophysics struggled to explain how a single dying star could sustain 2 wildly different pulsation clocks simultaneously without ripping itself apart. Theorists debated whether the slow pulse was caused by deep convective boiling or the gravitational drag of a hidden secondary object. For decades, proving the existence of a partner seemed technically impossible. Betelgeuse radiates more than 100,000 times the luminosity of our Sun, blinding our most sophisticated telescopes. Hunting for a dimmer companion in its immediate vicinity was the optical equivalent of trying to spot a glowing matchstick floating millimeters away from an industrial searchlight. Then came the calculated alignment of December 2024. Modeling suggested the theoretical secondary star would reach its maximum physical separation from the supergiant, offering a razor-thin observational window. Using ultra-high contrast coronagraphic instruments in the Atacama Desert, researchers targeted the coordinates to resolve whether this ghost star truly existed. What appeared on the sensors shattered previous assumptions about how red supergiants interact with their immediate stellar environment. The imaging data verified the presence of an authentic stellar companion designated Betelgeuse b. It was not a burnt-out stellar core or a planetary body. It is a genuine active main-sequence star. Astrophysicists were stunned by its physical mass. Theoretical calculations had predicted that if a companion existed, it would likely be a low-mass dwarf, perhaps comparable to or smaller than our Sun. The high-contrast data revealed that Betelgeuse b possesses a mass between 2 and 3 solar masses. That extra heft is the exact reason our instruments could detect it against the blinding glare of the host star. Had it been the modest size theorists initially assumed, the processing algorithms would have scrubbed its faint signature right out of the background noise. This companion does not sit comfortably in a distant, safe orbit. Its orbital path brings it into direct contact with the diffuse, extended atmosphere of the red supergiant itself. The smaller star is effectively submerged within the outermost gas envelopes shed by Betelgeuse. As Betelgeuse b barrels along its orbital trajectory, its gravitational pull gathers the loose stellar plasma around it. This drag creates a continuous high-density wake trailing behind the companion. Much like the churning water behind a cargo ship steaming through a narrow bay, space telescopes examining ultraviolet and infrared emissions detected this structural distortion running through the supergiant's outer atmospheric layers. This discovery provides a clean, elegant explanation for the mysterious 6-year brightness cycle that puzzled astronomers for decades. As Betelgeuse b completes its orbital circuit, it gravitationally sweeps through the dusty circumstellar environment. When it swings along the side facing Earth, it temporarily clears out lanes of obscuring dust grains, allowing more direct starlight to reach our telescopes. When it moves to the far side of its orbit, the dust reconvenes, subtly dimming the light reaching Earth. The 6-year rhythm is not an internal heartbeat of Betelgeuse at all. It is the physical orbital period of a multisolar mass companion dragging its way through a sea of surrounding plasma. Resolving that century-old puzzle changes our understanding of the star's dynamic evolution, but grasping why this companion remained invisible for so long requires stepping directly into the sheer intuition-breaking physics of red supergiant scales. Human intuition completely breaks down when dealing with objects of this volume. When we picture a star, we default to the Sun, a dense, sharply defined ball of incandescent plasma with a crisp edge. Red supergiants do not look or behave like that. Think of our Sun as a tightly wound golf ball made of dense, hot glass. Betelgeuse, by comparison, is less like a solid sphere and more like a suspended cloud of luminous fog the size of an entire planetary system, held together by a tenuous gravitational grip. Its outer atmospheric density is thousands of times lower than the air you are breathing right now in your room. If you were flying a spacecraft through its outermost layers, you would not encounter a hard surface. You would simply register a gradual increase in ambient temperature and a gentle rise in diffuse gas resistance. This low density makes the entire star astonishingly squishy and unstable. Deep inside its interior, massive boiling cells called convection currents churn continuously. On our Sun, convection granules are roughly the size of Texas or Alaska, boiling up and cooling down over minutes. On Betelgeuse, a single convection cell can span hundreds of millions of kilometers larger than the entire distance between the Earth and the Sun. A solitary bubble of superheated gas rising from the core can cover 20 to 30% of the star's visible hemisphere. Now imagine placing a heavy, compact object with 3 times the mass of the Sun inside that churning, gossamer envelope. The physical scale of this system defies everyday visualization. Picture an Olympic-sized swimming pool filled entirely with thick, swirling, incandescent foam. Now picture a solid, heavy steel cannonball whipping around the perimeter of that pool, skimming just beneath the surface of the suds. The cannonball does not merely move through the foam. Its immense mass pulls the foam inward, creating swirling vortexes, throwing massive ripples across the entire surface and destabilizing the delicate bubbles rising from below. That is what makes Betelgeuse b so disruptive. It is a dense gravitational hammer swinging through an ultra-fragile planetary-scale ocean of superheated gas. The interaction forces us to reconsider how energy and mass move from the star's deep core to its exterior boundaries. To understand how these two bodies interact, you have to look closely at the physics of mass loss in dying supergiants. Every star maintains a delicate structural balance throughout its life known as hydrostatic equilibrium. The inward crush of gravity generated by the star's enormous mass is constantly pushed back by the outward thermal pressure created by nuclear fusion occurring in its core. In our Sun, this balance is stable and will remain so for billions of years. But Betelgeuse has already burned through its core hydrogen and is currently fusing heavier elements in concentric shells around an increasingly dense core. Because the energy output from these burning shells is immense, the outer layers have been pushed out into deep space, where gravity has a much weaker hold on them. At these immense distances from the center, the outer gas cools to temperatures where heavier elements like carbon, oxygen, and silicon can actually condense into tiny, solid microscopic dust grains. Once these solid grains form, the intense radiation pressure streaming out from the star's core strikes them like a physical wind, pushing the dust away into the interstellar void. As the dust is blown outward, it drags the surrounding gas along with it. This continuous process forms an expanding stellar wind, stripping away material equivalent to the mass of Earth every few years. This brings us to the shocking event of late 2019, the Great Dimming. Astronomers tracking the star watched in real time as its visible brightness collapsed by more than 60% over a matter of weeks. The cause was a phenomenon known as a surface mass ejection. A titanic bubble of buoyant plasma rose from the deep interior, propelled by powerful convective motion. When it breached the surface, it blasted an enormous plume of hot gas outward into space at over 300,000 kilometers per hour. This was not an ordinary solar flare. The mass ejected in that single violent belch was several times the mass of our moon. As this giant plume traveled outward, moving millions of kilometers away from the star's heat, It underwent rapid cooling. The gaseous elements within the plume swiftly condensed into an enormous opaque curtain of soot-like silicate dust. Because this dust cloud was ejected directly along our line of sight to Earth, it acted as a massive stellar shade, blocking over 2/3 of the star's optical light. When we looked up at Orion in early 2020, we were not seeing a dying star fading out. We were looking through a freshly blown shroud of cosmic ash. But this raises a radical hypothesis. What if that colossal eruption was not an accident? The most provocative question in modern stellar astronomy is whether the companion star actively triggered that historic 2019 eruption. According to several astrophysicists studying the orbital dynamics, the timing of Betelgeuse B's closest atmospheric approach aligns intriguingly with the build-up to the Great Dimming. When a compact star of 2 to 3 solar masses sweeps through the fragile outer convective layers of a supergiant, its localized gravitational field exerts intense tidal forces on the rising gas below. Imagine a massive convective cell already surging toward the surface like a colossal tectonic upwelling. If a secondary gravitational body passes directly overhead at that critical juncture, its pull can dramatically lower the local escape velocity. Instead of the buoyant bubble rising, cooling, and circulating back downward into the star's interior, the companion's gravitational tug could have pulled the trigger, effectively ripping the top off the convective cell and hurling it out into open space. If this tidal trigger model is supported by ongoing simulations, it fundamentally rewires our understanding of how massive binary systems terminate their lifespans. We have long treated stellar mass loss in red supergiants as a purely internal, chaotic process driven solely by core thermodynamics. But in this scenario, mass loss becomes an externally modulated event, driven on a predictable orbital clock. Furthermore, some researchers have put forward an even more dramatic proposition. Betelgeuse B could actively alter how and when Betelgeuse undergoes its inevitable core collapse. As the companion continues to plow through the supergiant's atmosphere, it gradually transfers orbital energy to the surrounding gas, bleeding its own velocity through dynamical friction. Over cosmic timescales, this drag causes the companion's orbit to slowly decay, pulling it deeper into the host star. Under certain theoretical conditions, this orbital decay could culminate in a direct merger. If a 3 solar mass star plunges into the core of a dying red supergiant, the sudden injection of mass and angular momentum would violently disrupt the burning shells, potentially accelerating the final timeline toward a core collapse supernova. However, before we jump to conclusions about an imminent cosmic collision, we have to look at the serious counter-arguments and physical constraints raised by other researchers in the astronomical community. Not every astrophysicist is convinced that the companion star is the primary engine driving these dramatic eruptions. A healthy faction of observational astronomers and theoretical modelers urge significant caution, pointing out several major hurdles in the binary interaction theory. First, there is the fundamental issue of energy scale and localized convective chaos. Hydrodynamic simulations of red supergiant interiors show that these massive stars are inherently violent on their own, completely independent of external gravitational influences. Convective plumes in stars with 15 to 20 times the mass of our Sun carry kinetic energy figures that dwarf the localized tidal tug of a passing companion. Critics argue that the 2019 surface mass ejection could easily have been a purely stochastic, random internal event, a rare alignment of multiple internal convective bubbles that coincidentally broke through the surface at the same time. Second, the exact orbital parameters of Betelgeuse B remain subject to refinement. Resolving a faint point source within the glare of an immense, irregularly shaped supergiant, pushing the physical diffraction limits of our instruments, introduces potential measurement uncertainties. Some researchers have pointed out that the complex, constantly shifting surface features of Betelgeuse, such as giant, bright, convective hotspots, can occasionally mimic the appearance of a secondary companion when processed through contrast-enhancing algorithms. There is also the question of dust formation timescales. For a tidal pull to trigger an ejection that subsequently condenses into a line-of-sight dust cloud, the geometry must be exceptionally precise. The ejection must occur precisely along the vector pointing toward Earth, with the cooling gas reaching condensation temperature exactly when the cloud sits between the star's photocenter and our terrestrial telescopes. If the companion orbits in a tilted plane relative to our viewing angle, its tidal wake would push material off in directions that would never obscure the star's face from our vantage point. These competing viewpoints serve as an essential reality check. Science does not operate on runaway hype, it operates on reproducible physical evidence. While the binary companion hypothesis elegantly resolves the long-standing secondary pulsation period, linking it directly as the definitive cause of the Great Dimming remains an active, fiercely debated scientific investigation. To understand what is truly settled, we must examine the concrete observational facts verified across independent observatories. Stripping away the theoretical debates leaves us with a core set of indisputable, verified discoveries that have fundamentally advanced stellar physics. We know with certainty that Betelgeuse survived the 2019 event without suffering internal collapse. Multi-wavelength photometry tracked the star's steady recovery through late 2020 and 2021 as the obscuring dust cloud dissipated and expanded into the surrounding interstellar medium. By measuring the infrared re-radiation of that expanding shell, space observatories calculated the physical composition of the ejected material, confirming it was rich in silicon and oxygen dust grains. This provided direct, real-time observational confirmation of how dying supergiants enriched the surrounding galaxy with the chemical building blocks necessary for future generations of rocky planets. Additionally, the physical detection of a secondary light source at the predicted orbital separation confirms that Betelgeuse is not a solitary system. Combining optical data with long baseline radio interferometry from facilities like the ALMA array in Chile has allowed astronomers to construct a three-dimensional model of the star's outer gas dynamics. ALMA's radio eyes mapped the asymmetrical distribution of cool gas around the supergiant, revealing physical distortions and structural ripples that match the presence of an orbiting gravitational perturber. We have also established precise, safe boundaries regarding what an eventual supernova means for life on Earth. A core collapse supernova within our galactic neighborhood naturally triggers questions about biosphere safety. High-energy astrophysical calculations show that for a supernova to cause severe damage to Earth's protective ozone layer via ionizing gamma rays and energetic cosmic rays, the explosion would need to occur within roughly 160 light-years of our solar system. At a distance of approximately 650 light-years, Betelgeuse sits more than 4 times further than that hazard threshold. The radiation reaching our planet will be completely harmless to our atmosphere and technological infrastructure. When the core collapse eventually occurs, Earth will not experience a dangerous apocalyptic catastrophe. Our planet will simply enjoy the most luminous, spectacular celestial display in recorded human history. Following the verification of the companion star, observational campaigns worldwide have pivoted to monitor the Betelgeuse system across the entire electromagnetic spectrum. The James Webb Space Telescope has emerged as a cornerstone of this new observational phase. Because Webb operates primarily in the near and mid-infrared bands, it possesses a unique capability. It can look straight through the thick, obscuring curtains of dust that blind optical telescopes. Webb's high-resolution instruments are currently mapping the complex architecture of concentric dust shells surrounding Betelgeuse out to massive distances. These shells act like the growth rings of a colossal tree, preserving a historical timeline of every major mass ejection the star has experienced over the past tens of thousands of years. By analyzing the spacing and chemical profiles of these historical shells, astronomers can determine whether massive ejections occur on regular, predictable cycles tied to the companion's orbit, or whether they represent erratic, chaotic spasms of the dying supergiant. At the same time, next-generation ground-based facilities are preparing to join the hunt. The upcoming Extremely Large Telescope, ELT, currently under construction on the mountain Cerro Armazones in Chile, will feature a primary mirror spanning 39 meters in diameter. Its angular resolution will surpass current instruments by an order of magnitude. When the ELT turns its massive aperture toward Orion, it will be capable of resolving Betelgeuse B directly with unprecedented spatial clarity, tracking its orbital velocity and atmospheric wake month by month without relying on extreme algorithmic image reconstruction. Meanwhile, astrophysicists are closely watching for the companion's next orbital milestones. As Betelgeuse B continues its journey along its 6-year path, teams will measure the precise moment it transitions behind the star and emerges on the other side. This data will refine the companion's mass, orbital inclination, and exact gravitational drag, finally resolving the dispute over whether it can physically disrupt the internal convective balance of the host star. These upcoming measurements will settle the remaining debates about the companion's dynamic influence, leading us directly back to the ultimate question that started this entire investigation. This brings us back to the central puzzle that has captivated astronomers for generations. When will Betelgeuse finally reach its dramatic end? The definitive answer is that the star's core collapse remains unpredictable on human timescales. Current evolutionary models estimate that Betelgeuse will detonate as a Type II core collapse supernova anywhere between tomorrow night and 100,000 years from now. In astronomical terms, that range represents the blink of an eye. In human terms, it spans the entirety of modern civilization. When the moment arrives, the physics will unfold with staggering speed. The star's iron-rich core will collapse in a fraction of a second, shrinking from a sphere roughly the size of the Earth down into an ultra-dense neutron star barely 20 kilometers across. The resulting shockwave will rip through the outer envelope, unleashing a flash of light so intensely bright that the supernova will be visible in broad daylight for months, casting noticeable shadows on the ground at night and shining with the brilliance of a crescent moon. Yet there is a profound temporal reality at the center of this story. Because Betelgeuse sits 650 light-years away, the light reaching our eyes tonight left that massive red sphere during the 14th century, when medieval societies were only just beginning to map the world. If the core of Betelgeuse collapsed yesterday, or a century ago, the light bearing that news is currently traveling across the vast, frozen gulf of interstellar space at 300,000 kilometers per second. The grand cosmic finale may already be on its way to Earth right now, racing silently through the dark, waiting for the exact moment it transforms our night sky forever.